Imagine waking up one morning to headlines declaring that humanity's greatest question had finally been answered, not by a science fiction novel or conspiracy theory, but by the cold, undeniable evidence of a telescope orbiting 1,000,000 miles from Earth. For centuries, we've looked to the night sky and wondered if we were truly alone. Philosophers speculated, astronomers searched, and generations of dreamers hoped that somewhere beyond the pinpricks of light scattered across the heavens, another world was breathing, growing, and alive. Now, for the first time in history, the evidence is here, and it's so compelling that even the most skeptical scientists are struggling to dismiss it. The James Webb Space Telescope, humanity's most advanced eye in the cosmos, has returned data that may shatter the illusion of cosmic solitude forever. Hidden in a constellation 120 light-years away lies a planet so extraordinary it forces us to rethink what habitable even means. A world that is not just capable of supporting life, but may actually be more welcoming to it than our own fragile Earth. This planet, designated K20YTB, is unlike anything we expected. For decades, astronomers searched for Earth's twin, a rocky sphere, roughly our size, orbiting a sun-like star in the perfect sweet spot for liquid water. We believed that to find life, we had to find ourselves reflected in the stars, but the discovery of K20YTB obliterates that assumption. Here is a super-Earth, larger and heavier than our home world, cloaked not in the familiar mix of nitrogen and oxygen, but in a dense hydrogen-rich atmosphere that acts like a planetary greenhouse, wrapping the surface in stable, life-friendly warmth. Its most astonishing feature is its consistency. Across its vast expanse, the temperature holds steady at around 120 degrees Fahrenheit, hot but survivable, the kind of warmth that can accelerate the chemistry of life without destroying it. Unlike Earth, where climates vary wildly between poles and equator, day and night, this alien world enjoys a kind of cosmic equilibrium, a balance that seems almost too perfect to be coincidence. But temperature alone doesn't make the headlines. What truly stunned the scientific community was a single, nearly impossible signal buried within terabytes of data: dimethyl sulfide. On Earth, this molecule has one known origin: life itself, tiny plankton drifting through our oceans. Certain algae and even some bacteria produce it as a byproduct of metabolism. No volcano, no chemical reaction, no geological quirk has ever been shown to create it without the hand of biology. To detect it in the atmosphere of a distant planet is not just exciting, it is earth-shaking. And Webb didn't find it as a trace whisper, but as a clear and measurable signal strong enough to rule out error with a confidence level of 99.7%. To put that in perspective, scientists now place the odds of this detection being a fluke at just 3 in 1,000. That is as close to certainty as astronomy has ever dared to tread. And yet, this is not just a sterile set of numbers. It's the story of a world that challenges every assumption we've made about where life can thrive. K20YTB orbits a red dwarf star, smaller and cooler than our Sun, but far more stable. A star that could burn for trillions of years. Imagine life with unlimited time to evolve, unthreatened by the ticking clock that counts down our own Sun's lifespan. Imagine oceans infused with hydrogen, stretching hundreds of miles deep, creating habitats for creatures unlike anything Earth has ever known. Imagine a biosphere so vast, so productive, that it shapes the very chemistry of its skies just as ours does on Earth. The question that once seemed unanswerable suddenly feels like it has always had an inevitable answer. Life, it seems, is not the exception in the universe. It may be the rule. And if a planet 120 light-years away can send us such an unambiguous signature, then perhaps this is only the beginning. Perhaps, hidden among the billions of stars in our galaxy, there are countless other worlds breathing in their own strange ways, waiting for us to notice. This isn't just science. It's the moment humanity crosses a threshold. From wondering to knowing, from being an isolated species to being part of a cosmic community we've only just begun to glimpse. The discovery of K2118b doesn't just change astronomy, it changes us forever. The first real hint that something extraordinary was waiting to be uncovered arrived not with a thunderous announcement, but quietly, on a cold December morning, in a lab at Cambridge University. Niku Madusan, an astronomer who had devoted his life to analyzing the faint whispers of light from distant worlds, sat in front of his computer screen, eyes fixed on a stream of data flowing from the James Webb Space Telescope. Webb had been scanning a planet designated K2018b, a super-Earth orbiting a red dwarf star in the constellation Leo, some 120 light-years away. To most people, the data looked meaningless, just rows of numbers and jagged lines that reflected tiny dips in light as the planet passed in front of its star. But to Madusan and his team, those faint signals carried the fingerprints of an alien world, and hidden in them was something that would rewrite everything humanity thought it knew about life in the universe. At first, the readings seemed routine: water vapor, methane, carbon dioxide, all fascinating in their own right, but not enough to prove anything beyond the fact that K2018b had an atmosphere thick with potential. Then came the spike, an absorption pattern so sharp and so impossible that it made Madusan's hands tremble. Dimethyl sulfide, a molecule so peculiar that on Earth it is only ever produced by living organisms. To understand the magnitude of this finding, you need to appreciate how astronomy works. Detecting life on a distant planet is not like snapping a photograph of alien forests or oceans. Instead, scientists analyze the light of a star as it filters through the thin veil of a planet's atmosphere. Certain molecules absorb light at very specific wavelengths, leaving telltale dark line spectral signatures that act like a cosmic barcode. Each line corresponds to a unique molecule, and together they form a chemical fingerprint of the atmosphere. In the case of K2118b, Webb's ultra-sensitive instruments picked up the unmistakable signature of dimethyl sulfide. On Earth, this compound comes from plankton in the oceans, some types of bacteria, and algae. There is no known geological or chemical process that creates it without life. And Webb did not just detect a faint trace that could be dismissed as error. The data revealed concentrations strong enough to register across the unimaginable gulf of space, a biosignature so bold it was like a flare sent across the cosmos. Madusan's first reaction was disbelief. For decades, scientists had dreamed of this exact moment, but it always seemed impossibly far away, something for future generations to discover. Astronomers had often spoken of the Great Silence, the haunting fact that despite decades of searching, humanity had never found definitive proof of life beyond Earth. Now, on his computer screen, Madusan was staring at the end of that silence. The numbers did not lie. Statistical analysis showed a 99.7% confidence level, nearly 3 in 1,000 odds, that the detection was a fluke. In the cautious language of science, this was as close to certainty as one could get without direct visual evidence. This wasn't speculation, it was a signal, it was life. But what made the discovery even more staggering was the planet itself. K2118b was no twin of Earth. For decades, astronomers had searched for a world as close as possible to our own, a rocky planet orbiting a sun-like star at just the right distance for liquid water. Yet K2118b was larger, heavier, wrapped in a dense hydrogen-rich atmosphere that behaved nothing like the nitrogen-oxygen blanket surrounding our own planet. At first glance, such an environment seemed hostile, perhaps even poisonous to life as we know it. Yet the very qualities that made it alien turned out to be what made it uniquely habitable. The hydrogen acted as an insulating blanket, distributing heat evenly across the surface. Instead of wild swings between day and night, pole and equator, the planet maintained a steady warmth of about 120 degrees Fahrenheit, a temperature that was not only survivable but ideal for supporting biological processes. For Madison and his colleagues, this was more than coincidence. It was a sign that life could not only survive, but flourish in conditions once thought impossible. The moment the signal was confirmed, everything changed. Within hours, messages were flying across research teams, data was double-checked and triple-checked, and computer algorithms were run again and again to rule out contamination or instrument error. Each time, the conclusion held. Dimethyl sulfide was there, strong and undeniable, shaping the atmosphere of K2-18b just as it does on Earth. The implications were staggering. If life could exist on a super-Earth, wrapped in hydrogen clouds, then the universe was far more generous with habitability than anyone had dared to hope. This was not just a planet with life. It was proof that biology could emerge under conditions humanity had barely considered. The silence of the cosmos had finally been broken, and it began not with a booming revelation, but with one trembling scientist staring at a line of light from 120 light-years away, realizing that he had just glimpsed the breath of another world. The discovery of life on K2-18b did not just rest on the dimethyl sulfide signature. It was also tied to the nature of the star it orbits. K2-18, a red dwarf that at first glance would seem unremarkable, even hostile compared to our own sun. Red dwarfs are the most common type of star in the galaxy, accounting for nearly 3/4 of all stellar bodies, yet for decades they were overlooked in the search for habitable worlds. The assumption was simple: these stars are smaller, cooler, and dimmer than the sun, and the planets orbiting close enough to receive warmth would be subject to tidal locking and violent stellar flares. But K2-18 turned out to be different, and its stability may prove to be the key to the greatest discovery in human history. Unlike many of its kind, K2-18 is unusually quiet, producing minimal flare activity. That means its planets are spared from the deadly radiation bursts that could strip away atmospheres or sterilize surfaces. Instead, the energy from K2-18 arrives in steady, reliable doses, feeding K2-18b with just the right amount of light and heat to maintain its delicate balance. While our sun will eventually expand into a red giant, scorching Earth and reducing it to a cinder within 5 billion years, red dwarfs like K2-18 can burn steadily for trillions of years, lifespans longer than the current age of the universe. That gives any life orbiting them an almost unlimited timescale to evolve complexity, stability, and possibly intelligence far beyond what we know. This stellar environment also redefines what scientists thought was necessary for habitability. For decades, the Goldilocks zone was calculated around sun-like stars based on distances where liquid water could exist. But in the case of K2-18b, the rules have changed. Its orbit is incredibly tight, completing a year in just 33 Earth days. Yet, because K2-18 shines with less energy than the Sun, that close orbit actually puts the planet squarely in the habitable zone. To a distant observer, it would appear as if K2-18b were hugging its star dangerously close, but in reality, it receives nearly the same amount of energy per square meter as Earth does. This coincidence allows it to maintain temperatures hovering around 120 VFDAF, warm but stable, without the runaway heating of Venus or the icy desolation of Mars. For the first time, astronomers realized that a planet orbiting a red dwarf could be not only habitable, but potentially more life-friendly than Earth itself. Another remarkable aspect is the effect of tidal locking, where one side of the planet always faces the star while the other remains in perpetual darkness. At first glance, this seems like a fatal flaw. The day side could be scorched, while the night side could freeze into lifelessness. Yet K2-b's thick hydrogen atmosphere smooths out this imbalance, transporting heat across the globe and keeping both hemispheres warm enough for liquid water. This means that both the eternal day and eternal night could host stable environments, vastly increasing the potential surface area where life could thrive. Earth, with its seasonal changes, ice ages, and climate fluctuations, has forced life to adapt through cycles of stress and catastrophe. K2-b, by contrast, offers a planet-wide equilibrium, an alien world where conditions remain stable for unimaginably long timescales. Life there would not just survive, it would flourish under consistency. The implications extend even further. If life thrives around red dwarfs, the number of potentially habitable planets in the galaxy is far higher than previously believed. These stars are not rare gems like sun-like stars, but the galactic norm, filling the spiral arms of the Milky Way with billions upon billions of systems. For every star like our Sun, there are dozens of red dwarfs, many with their own retinue of planets. Suddenly the odds are no longer slim. K2-b proves that we should not be searching for Earth's twin, but Earth's stranger cousins, worlds orbiting dim, long-lived stars under conditions once dismissed as hostile. This realization is a turning point. The very environments astronomers used to ignore might now be the most promising cradles of life. As Niku Madusan prepared to release the findings, he understood the magnitude of what the red dwarf system represented. This was no isolated anomaly, no lucky accident. It was a template. If one red dwarf star could host a super-Earth teeming with life, then countless others could as well. The silence of the cosmos was not because life was rare, but because humanity had been looking in the wrong places. The real promise was not in stars like our Sun, but in the quiet, unassuming red dwarfs that would outlive every star we can see today. K2-19 was no longer just a dim point in the constellation Leo. It was a cosmic lighthouse, showing us that life may not just exist elsewhere. It may be everywhere, waiting patiently around the smallest stars in the universe. K2-b is not just another exoplanet orbiting a distant star. It belongs to a special class of worlds called super-Earths, planets larger than our own, but smaller than Neptune. For a long time, astronomers dismissed these planets as inhospitable, assuming their size meant they were little more than mini gas giants, too dense and too hot to sustain life as we know it. But the James Webb Space Telescope shattered those assumptions when it revealed that K2-b has the perfect combination of mass, atmosphere, and chemistry to not only support life, but potentially sustain it on a scale Earth could never match. With a mass approximately 8.6 times greater than Earth's, K2-b has a gravitational pull nearly 3 times stronger than what we experience here. At first, this might sound like a crushing disadvantage, but in reality, it's a life-sustaining blessing. That immense gravity holds onto its thick hydrogen-rich atmosphere with unyielding strength, preventing it from being stripped away by stellar winds or cosmic radiation. Unlike Mars, which lost its atmosphere billions of years ago and became a barren desert, K2-b has the stability to preserve its gases for trillions of years, creating a protective blanket that fosters equilibrium and shields life from extinction-level threats. This thick atmosphere also does something remarkable. It redistributes heat across the entire planet, ensuring that even the perpetual night side, the hemisphere locked away from its red dwarf star, remains warm enough to host liquid water. On Earth, temperature swings create cycles of scarcity and abundance, forcing organisms to adapt, migrate, or perish. On K2-b, the climate is astonishingly uniform. The hydrogen greenhouse effect maintains a stable surface temperature of around 120 BFF, a range that not only allows water to stay liquid, but also accelerates biological processes without destroying delicate molecular structures. It's a world where the challenges of survival would not be about enduring seasonal shifts or planetary catastrophes, but about thriving in a consistent, planet-wide environment. Life there would have the luxury of stability, able to evolve complexity without constant setbacks. The composition of the atmosphere adds even more intrigue. Instead of nitrogen and oxygen like Earth, K218b's skies are dominated by hydrogen and helium, with powerful traces of water vapor, carbon dioxide, methane, and, most importantly, dimethyl sulfide, the molecule that cracked open the door to confirmation of alien biology. The sheer abundance of these gases points to a biosphere operating at planetary scale. On Earth, methane is quickly broken down by sunlight, meaning its continued presence requires constant replenishment by life forms, whether from bacteria in wetlands or digestive processes in animals. The fact that methane is so plentiful on K218b suggests organisms are actively producing it in staggering amounts, turning the atmosphere into a chemical fingerprint of thriving biology. And then there is dimethyl sulfide, a molecule so tightly bound to life that it has no known non-biological source. On Earth, it is created by phytoplankton and bacteria in the oceans. On K218b, its detection means that oceans, or ocean-like environments, must be producing it in volumes large enough to alter the chemistry of an entire planet. The implications are staggering. A world this massive, with oceans hundreds of miles deep, could host ecosystems that make Earth's biosphere look small by comparison. Imagine an ocean that stretches from pole to pole, layered with environments shaped by depth, pressure, and chemical gradients. On Earth, even the deepest trenches host microbial life, despite crushing pressure and freezing darkness. On K218b, the vastness and stability of the oceans might allow for life not only at the surface, but throughout the entire water column. Entire ecosystems could exist at depths unimaginable here, evolving into complexities that dwarf our understanding of biology. The pressure that would crush an earthly submarine might be perfectly tolerable for alien organisms, built to thrive in environments dominated by hydrogen and high gravity. The presence of dimethyl sulfide suggests that life on K218b has already gone beyond microbial beginnings. For concentrations strong enough to be detected from 120 light-years away, the biosphere must be enormous, with biological processes operating at industrial scales. This isn't a handful of microbes clinging to survival in some isolated niche. This is a planet alive from its oceans to its skies, exhaling molecules into the atmosphere that transform the chemistry of the entire world. More astonishingly, the absence of certain molecules, like ammonia, reinforces this. If K218b were just a lifeless gas giant, ammonia would be expected in abundance. Its near absence indicates active biology is consuming or altering it, just as Earth's life maintains oxygen and methane in delicate balance. K218b forces us to redefine what habitable means. It is not Earth's twin, nor does it need to be. Its gravity, size, and hydrogen envelope once made it seem too alien for life. But now those same traits are what make it stable, fertile, and abundant. Instead of showing us how rare Earth is, K218b reveals that life might thrive in environments radically different from what we imagined. Super-Earths may not be inhospitable oddities, but the galaxy's best laboratories for biology. If life is thriving there, then the billions of other super-Earths scattered throughout the Milky Way may also be alive. The truth is humbling. Earth may not be the gold standard for habitability, but simply one example among countless living worlds. In K218b's alien skies and hydrogen seas, the universe is whispering a message we are only beginning to understand. Life is not an exception, it is the rule. The star at the center of K218b's story is not a blazing giant like our sun, but a modest red dwarf, smaller, cooler, and dimmer than what we're used to. At first glance, that might seem like a disadvantage. After all, for decades, astronomers assumed the best chance of finding life was around sun-like stars, worlds bathed in light similar to our own. But the reality is far more fascinating. Red dwarfs are the most common type of star in the galaxy, making up nearly 3/4 of all stars, and unlike our sun, which will burn for about 10 billion years before swelling into a red giant and destroying everything in its orbit, red dwarfs burn slowly and steadily for trillions of years. That stability means any planet orbiting in their habitable zones could have time scales for life that make Earth's 4 billion years of evolution look like a blink of an eye. K2018b, circling its star in the perfect Goldilocks zone, may not just be habitable, it may have had an eternity for life to flourish and evolve into something more complex than anything we can imagine. One of the most remarkable aspects of K2018b's orbit is that it lies so close to its star that a year there lasts just 33 Earth days. To us, that sounds extreme, but because the star is cooler and less luminous, the planet receives about the same energy per square meter as Earth gets from the sun. This cosmic coincidence creates conditions surprisingly similar to our own, but with one key difference: K2018b is tidally locked. This means one side of the planet always faces the star, basking in eternal daylight, while the other side remains in perpetual darkness. On Earth, such an arrangement would be catastrophic. One side would scorch while the other froze solid, but K2018b's thick hydrogen-rich atmosphere saves it. Like a giant thermal blanket, it efficiently redistributes heat across the entire surface, keeping both the day side and the night side at a stable weather. This planetary balance eliminates the violent extremes of climate, creating a world where conditions are more stable than Earth's seasonal cycles. Life on such a planet would never face winter, drought, or ice ages. Instead, it would evolve in an environment of near-perfect stability. The red dwarf star itself adds another fascinating layer. Many red dwarfs are known for violent stellar flares, sudden outbursts that can blast nearby planets with lethal radiation, potentially stripping away atmospheres and sterilizing surfaces. But K2018, the star at the heart of this system, appears to be unusually quiet. Its relatively calm nature means K2018b's atmosphere remains intact, shielded from the worst of cosmic weather. And even when flares do occur, the planet's dense atmosphere acts as a natural barrier, absorbing harmful radiation before it can reach the surface. This dual protection, the star's stability and the atmosphere's shielding, creates one of the safest stellar environments possible for the evolution of complex biology. The longevity of red dwarfs cannot be overstated. Our sun, though massive and bright, is ultimately fleeting. In a few billion years, its expansion will end life on Earth, no matter what we do. But red dwarfs like K2018 will continue burning calmly for trillions of years. That means K2018b has not just billions, but trillions of years for life to evolve. If Earth required nearly 4 billion years to produce humans, imagine what could happen with timescales 1,000 times longer. Entire civilizations could rise and fall, evolve into forms beyond comprehension, and still have more time left than humanity has ever known. K2018b may be not just habitable but unimaginably ancient in terms of biological development, a living world that has had time to explore evolutionary paths our planet never had the chance to take. What makes this scenario even more intriguing is the universality of red dwarfs. Because they are so common, and because their habitable zones are so close to their stars, the odds of finding more planets like K2018b are staggeringly high. Every red dwarf we look at could host a super-Earth in just the right orbit, wrapped in thick atmospheres and heated to life-friendly temperatures. Instead of being rare, life-bearing planets might be scattered everywhere, orbiting the most ordinary and abundant stars in the galaxy. In fact, astronomers now believe that the majority of habitable planets in the universe may orbit red dwarfs rather than sun-like stars. This realization completely rewrites our expectations. Life may not be fragile, clinging desperately to rare Earth-like worlds. It may be abundant, thriving in systems we once overlooked. K2-18b's relationship with its star also teaches us something profound about the adaptability of life. For generations, humanity assumed that our sun was the perfect life giver, and that Earth was a unique balance of distance, temperature, and atmosphere. But the discovery of K2-18b proves that life can emerge under conditions we once dismissed as alien and impossible. A smaller star, a tidally locked orbit, a hydrogen atmosphere, all of these seem to exclude habitability, yet, combined, they create one of the most life-friendly environments we've ever found. The stability of the star, the efficiency of the atmosphere, and the eternity of time all align to make K2-18b more than just another planet. It is a demonstration that the universe favors life in ways we are only beginning to understand. The story of K2-18b and its red dwarf star is not just about one planet, it's about a new vision of the cosmos itself. The universe is not filled with sterile rocks orbiting violent stars. It is filled with quiet, enduring red dwarfs, each one a potential cradle of life. K2-18b and its planet prove that we may not be looking for Earth's twin at all. Instead, we are discovering Earth's strange cousins, worlds orbiting dim red stars that burn forever, each one a living laboratory for biology. And if K2-18b is any indication, the universe is not just habitable, it is overwhelmingly alive. Temperature is the silent architect of life, the invisible hand that determines whether a planet can harbor living organisms or remain a barren rock adrift in the cosmos. On Earth, temperature governs everything from the circulation of oceans to the diversity of ecosystems, but here, variation is the rule. Seasons shift, nights chill, summers scorch, and the poles stand as frozen deserts, while the equator bakes in relentless heat. Life adapts, struggles, and sometimes fails under these constant changes. Yet on K2-18b, the James Webb Space Telescope revealed something so extraordinary, it challenged the very idea of what makes a world habitable, a surface temperature that remains locked at 20 degrees, not in one place, not in one season, but across the entire globe, day and night, pole to pole, with a stability that Earth has never known. This number, so deceptively simple, carries within it the story of a planet where life might not just exist, but thrive on a scale beyond our imagination. The balance is delicate and astonishing. K2-18b orbits its red dwarf star in such a way that it receives almost exactly the same amount of stellar energy per square meter as Earth receives from the Sun. By itself, that would suggest conditions comparable to our world, but Earth's thin nitrogen-dominated atmosphere allows heat to escape into space, leading to massive temperature fluctuations between night and day, summer and winter, or pole and equator. K2-18b, on the other hand, is wrapped in a thick hydrogen-rich atmosphere that functions as a colossal insulator. Hydrogen molecules trap infrared radiation with stunning efficiency, redistributing heat so thoroughly that even the planet's night side, which never sees its star due to tidal locking, remains warm enough to support liquid water. Instead of dramatic contrasts, the entire planet exists in equilibrium, a global greenhouse system that prevents freezing, boiling, or catastrophic storms. It is as if nature itself designed a thermostat set permanently at the ideal point for life. The significance of 120 BFU cannot be overstated. On Earth, we think of it as extreme temperatures you'd encounter in Death Valley on a dangerous summer day or in the scalding heat of a fevered human body. Yet biology has proven astonishingly resilient at this threshold. Microbial life on Earth thrives in hydrothermal vents at similar or higher temperatures, metabolizing chemicals in environments utterly hostile to most forms of life. Laboratory experiments have shown that complex biochemical processes function efficiently up to 2050 BFU, with 120 BFU lying in the sweet spot where reactions occur fast enough to sustain metabolism without destabilizing the delicate molecules that form the foundation of biology. For K218b, this means that life has an environment that maximizes chemical productivity while minimizing destructive extremes. More intriguingly, this constant temperature eliminates the survival pressures that shape much of life on Earth. Here, organisms are forced to migrate, hibernate, or evolve protective mechanisms to cope with constant changes. Entire species have perished because they could not adapt to sudden ice ages, heat waves, or volcanic winters. On K218b, life would be spared from these challenges. Evolution could focus not on survival against the elements, but on complexity, growth, and diversification. With no winter to endure or desert drought to survive, organisms could channel energy into developing intricate ecosystems, symbiotic relationships, and possibly intelligence. Life here would not be about endurance, it would be about flourishing. But the perfection of K218b's temperature lies not just in biology, it is also a triumph of planetary physics and chemistry. The red dwarf star provides steady, consistent energy over time, scales that dwarf the lifespan of our sun, ensuring the stability of incoming heat. The hydrogen-rich atmosphere captures and redistributes that energy evenly. Meanwhile, the planet's mass and gravity ensure that this thick atmosphere is not lost to space, unlike Mars, which bled its atmosphere away billions of years ago. Every piece of the puzzle aligns to produce an environment of unshakable thermal balance. It is not an accident, but a cosmic masterpiece, a planet where all forces conspire to maintain a world at the perfect temperature for life. The psychological effect of this discovery is staggering. On Earth, we have long assumed that our planet's diverse climates are the key to evolution, that the challenges of ice and fire, heat and cold created the dynamism necessary for intelligence to emerge. Yet K218b suggests the opposite could also be true. Stability might be the true key. A world where the climate never shifts, where oceans remain liquid everywhere, and where life never fears extinction from environmental swings, may nurture civilizations that reach heights far beyond ours. Perhaps intelligence on K218b is not only possible but inevitable, guided not by desperation but by abundance. In many ways, 120 VFTF is more than a number. It is a revelation about the universe's ability to create order and balance in places we once assumed were too alien for life. It tells us that habitability does not require Earth-like conditions at all. It can emerge in hydrogen skies, under dim red stars, and across worlds locked eternally to one face of light and one of darkness. For billions of years, Earth's temperatures have swung wildly, creating extinctions and upheavals, but on K218b, life has been given a perfect stage, lit by a quiet star wrapped in a protective blanket and set to a temperature that never wavers. If we ever needed proof that the cosmos is biased toward life, it is found in this number, 120 VFTF, the heartbeat of an alien world where life may already be thriving in comfort and abundance. Dimethyl sulfide might sound like the kind of obscure chemical you'd only ever encounter in a laboratory textbook, but to astronomers and astrobiologists, it has become one of the most extraordinary molecules ever detected. Its discovery in the atmosphere of K2-18b by the James Webb Space Telescope wasn't just another scientific milestone, it was a paradigm shift, a turning point that redefined humanity's understanding of its place in the cosmos. On Earth, dimethyl sulfide is intimately tied to life. It is produced almost exclusively by living organisms, particularly phytoplankton in the oceans. As these microscopic plants metabolize and thrive, they release dimethyl sulfide into the atmosphere, where it plays a role in cloud formation and climate regulation. No volcano, no mineral reaction, no geological process on Earth has ever been known to produce this molecule in significant quantities. That exclusivity makes dimethyl sulfide one of the most reliable biosignatures scientists could ever hope to find. And when Webb detected it 120 light-years away, the implications hit like a thunderclap. Life was not confined to Earth. Life had announced itself from across interstellar space. The first thing that makes this discovery so shocking is its certainty. In the realm of exoplanet research, most atmospheric detections are cautious, hedged with phrases like possible trace or tentative evidence, but the dimethyl sulfide signal on K2-18b was strong, clear, and statistically robust. The 99.7% confidence level meant the odds of the detection being an error were infinitesimally small, about 3 in 1,000. In science, where skepticism reigns and discoveries are overturned regularly, this level of confidence was unprecedented. For decades, scientists have argued about whether life would ever leave behind a clear enough atmospheric fingerprint to be seen from light years away. With dimethyl sulfide, that argument was settled. The universe had given us an unmistakable neon sign that read, "Life exists here." Equally remarkable was the abundance of the molecule. On Earth, dimethyl sulfide is present in the atmosphere in modest amounts, detectable but not overwhelming. On K2-18b, however, the concentrations observed were significantly higher than expected. This suggested that life on this world wasn't clinging to existence in isolated pockets. It was flourishing on a planetary scale. A biosphere vast and productive enough to release dimethyl sulfide into the skies of an entire planet implies oceans teeming with microbial life, or even ecosystems of complexity we can only begin to imagine. The discovery shattered the idea that extraterrestrial life would be fragile, rare, or hidden. Instead, it suggested abundance, strength, and influence powerful enough to alter atmospheric chemistry in ways visible across the gulf of space. The biochemical significance of dimethyl sulfide deepens the mystery. Its structure, involving sulfur atoms bound to carbon-based methyl groups, requires specific enzymes to form. On Earth, these enzymes evolved through intricate pathways over billions of years, entwined with the sulfur cycle that regulates atmospheric and oceanic chemistry. The fact that such a molecule exists on K2-18b suggests that evolution there followed similar chemical logic. In other words, life on K2-18b might not just be a bizarre alien curiosity, it might share universal traits with life on Earth. This idea, sometimes called convergent biochemistry, implies that wherever conditions allow, the same building blocks of life will assemble in predictable ways. Carbon, hydrogen, oxygen, nitrogen, sulfur, these elements may be the alphabet of life across the universe, spelling out biology in ways both familiar and alien. Yet, dimethyl sulfide's presence also hints at something deeper: ecological scale. For this molecule to accumulate in K2-18b's hydrogen-rich atmosphere, biological processes must be producing it continuously and in large amounts. Otherwise, it would quickly break down or disperse. This suggests not only that life exists, but that it is integrated into planetary processes. Just as Earth's atmosphere is actively maintained by the combined respiration of countless organisms, K-18b's air appears to be shaped by the breath of alien life. It's not a static, lifeless system. It's dynamic, evolving, and alive. The ramifications of this detection extend far beyond science. For centuries, humanity has wondered if it is alone. Philosophers speculated, religions debated, and scientists searched for signals that never came. Now, in the faint absorption lines of starlight passing through an alien atmosphere, the silence has been broken. Dimethyl sulfide is not just a molecule, it is a voice, faint but clear, telling us we are not the sole expression of life in the cosmos. It forces us to reconsider everything we assumed about rarity, isolation, and uniqueness. Life, it seems, may not be an improbable accident. It may be a universal outcome wherever chemistry and physics provide the right stage. Even more tantalizing is the possibility that dimethyl sulfide is only the beginning. If Webb can detect this molecule, then perhaps it can also uncover others, methane, oxygen, nitrogen compounds that hint at even more complex biological cycles. K-2018b's atmosphere could be full of chemical whispers waiting to be decoded, each one revealing another layer of its alien ecosystem. Perhaps the organisms producing dimethyl sulfide are not merely microbial, but part of intricate food webs stretching across alien oceans and continents. The story of this planet is only beginning to unfold, and dimethyl sulfide is its prologue. In the end, the detection of this molecule represents more than a scientific achievement. It is the first hard evidence that life is not Earth's exclusive domain. It tells us that across 120 light-years of empty space, another world is alive, its atmosphere breathing with the exhalations, countless unseen organisms. Dimethyl sulfide is a chemical, yes, but it is also a revelation, a promise, and perhaps the most profound discovery humanity has ever made. In science, certainty is a rare luxury. Most discoveries are tentative, expressed in probabilities, margins of error, and carefully hedged conclusions. Yet, when astronomers analyzed the James Webb Space Telescope's data on K-18b, what emerged was an almost shocking level of clarity: the detection of dimethyl sulfide, a molecule produced only by life, with a statistical confidence of 99.7%. To understand the weight of this number, consider what it really means. A 99.7% confidence level corresponds to what scientists call a 3 sigma detection, a standard so rigorous it's used in particle physics to confirm the discovery of subatomic particles and in astronomy to validate gravitational waves. It means that out of 1,000 chances, only 3 could produce the observed signal through noise, error, or coincidence. Imagine flipping a coin 1,000 times and landing on heads 99.87 times. That level of improbability illustrates why scientists consider this detection almost undeniable. In the cautious world of astrophysics, where extraordinary claims require extraordinary evidence, such a result borders on revolutionary. The faintness of the signal makes the achievement even more astonishing. Dimethyl sulfide appears in K-2018b's atmosphere in concentrations measured in parts per billion, yet Webb's instruments were able to identify it from 120 light-years away. That's equivalent to detecting the faintest whisper in the middle of a hurricane, or measuring the width of a human hair with the precision of a single atom. The telescope's infrared spectrographs separated the faint light passing through the planet's atmosphere into its constituent wavelengths, and each wavelength carried subtle fingerprints of molecules. Within those fingerprints was the unmistakable signature of dimethyl sulfide, appearing not once, but repeatedly across different observations, different instruments, and different wavelengths. The consistency was key. Independent lines of evidence converged to tell the same story. Statistical analysis left no stone unturned. Could the signal have been an artifact of Webb's instruments? Advanced algorithms checked for contamination, systemic errors, or false positives introduced by the telescope itself, and none were found. Could it have been an unknown chemical process unrelated to life? Models of atmospheric chemistry ruled that out, as no abiotic reaction could produce dimethyl sulfide in such abundance. Could it have been contamination from Earth? The distance alone made that impossible, and redundant data streams confirmed that the signal originated from K2118b, not from our planet. One by one, alternative explanations were eliminated until the only one left was biological production. The rarity of such certainty cannot be overstated. In the history of exoplanet research, most atmospheric detections hover at 1 or 2 sigma levels. Statistical confidence too low to make bold claims. A 99.7% detection is a leap forward, the difference between speculation and knowledge. Scientists have long warned the public against jumping to conclusions when it comes to life-found headlines, but in this case, many of those same scientists are themselves astonished at the strength of the data. This isn't just a possible biosignature. It's as close to proof as the tools of modern science can provide. The implications extend far beyond the specifics of K2118b. A 3 sigma detection sets a new standard for exoplanetary biosignatures, proving that humanity's instruments are capable of identifying life not by seeing alien organisms directly, but by analyzing their planetary scale effects. Just as oxygen and methane coexistence on Earth signals the presence of life, dimethyl sulfide on K2118b signals that alien biology is actively shaping its atmosphere. The level of certainty means this isn't a one-off anomaly, it's a demonstration of what our telescopes can do, opening the door to dozens, perhaps hundreds of similar discoveries in the coming years. And yet, perhaps the most profound implication is philosophical. For millennia, humans have asked whether we are alone in the universe. The answers were speculative, grounded in imagination rather than data. Now, with a confidence level of 99.7%, science has provided an answer as firm as any we have about the speed of light or the age of the Earth. The loneliness that has defined our cosmic perspective has been broken. Somewhere across the gulf of space, under alien skies and in hydrogen-rich air, life is breathing and producing molecules we can detect across interstellar distances. This certainty forces us to reevaluate our place in the cosmos. If life can be detected so clearly on one world orbiting a red dwarf star, what does that mean for the countless other planets waiting to be studied? Red dwarfs alone account for 3/4 of all stars in the galaxy. If one of them hosts life that announces itself so loudly in atmospheric chemistry, then it becomes increasingly likely that life is not rare, but abundant. The statistical confidence in this discovery does more than confirm one planet's vitality. It hints at a universe teeming with biology, where 3 sigma detections will soon become routine rather than extraordinary. Ultimately, the 99.7% confidence in dimethyl sulfide is more than a number. It is a threshold moment in human history. It transforms the question of extraterrestrial life from if to where else. It represents the crossing of a line from speculation to evidence, from dreaming to knowing. With this discovery, the universe has spoken in the language of numbers, probabilities, and light, and the message is clear. Life is not unique to Earth. Life exists beyond our world, and now we have the statistical certainty to prove it. The discovery of K2118b's hydrogen ocean marks one of the most extraordinary shifts in our understanding of habitable environments beyond Earth. For decades, astronomers have assumed that liquid water was the essential marker of habitability, but they imagined oceans like ours, vast salty expanses contained within rocky basins, limited in depth, pressure and chemistry by the conditions of a terrestrial planet. K218b challenges and expands this notion entirely. Its oceans are not just bodies of water, but immense hydrogen-enriched seas, hundreds of miles deep, existing under pressures that would crush any Earth-based submarine, yet remaining stable and life-friendly because of the unique chemistry of hydrogen and water interacting together. On Earth, the deepest trenches in the ocean experience crushing pressures 1,000 times greater than at sea level, conditions that limit most life to the surface or mid-ocean ranges. Yet on K218b, hydrogen dissolves into the water, altering its physical properties and creating a liquid medium that can remain stable across a far wider range of temperatures and pressures than pure water alone. This means that where Earth's life faces natural limits to where it can exist, K218b's biosphere might extend across depths unimaginable to us, with ecosystems evolving not in narrow niches, but in enormous, planet-spanning oceans. What makes this hydrogen ocean even more remarkable is its role as a planetary stabilizer. On Earth, our atmosphere slowly leaks into space, and over billions of years, this gradual loss of air and water will render our world uninhabitable. Mars experienced this fate long ago when its thin gravity allowed its atmosphere to escape, leaving behind a cold, desolate desert. K218b avoids this problem in a unique way. Its hydrogen ocean functions as an atmospheric reservoir, constantly replenishing the atmosphere as hydrogen is lost to space. This feedback system means that the planet could maintain a stable, thick atmosphere for trillions of years, ensuring habitability across time frames that dwarf the lifespan of our own solar system. Life on K218b would not just have a chance to emerge, it would have almost unlimited time to flourish and evolve complexity on a scale Earth has never allowed. The ocean's chemistry also provides a new energy pathway for life. On Earth, hydrogen is scarce, appearing in only trace amounts in our atmosphere, but a few microorganisms have evolved the ability to metabolize it. On K218b, however, hydrogen is abundant and constantly cycling between the ocean and atmosphere. Organisms there could breathe hydrogen in the same way we breathe oxygen, using it as a primary energy source. The result would be ecosystems built on a completely different biochemical foundation, invisible to many of our traditional detection methods, yet potentially even more prolific than Earth's. This explains why the detection of dimethyl sulfide in the atmosphere is so important. It is a biosignature that proves life exists despite being based on chemistry alien to us. The sheer scale of K218b's ocean also suggests evolutionary possibilities beyond our imagination. Earth's oceans are vast by our standards, but they pale in comparison to the hundreds of miles of liquid depth predicted for K218b. Within such a volume, ecosystems could evolve with diversity that dwarfs anything on Earth. There could be microscopic hydrogen-breathing organisms carpeting the ocean, massive filter feeders adapted to high pressures, or entire evolutionary pathways that lead to complex, multicellular organisms unbound by Earth's limitations. The stable temperatures created by the thick hydrogen atmosphere ensure that these oceans remain in liquid form across the planet, from the sunlit day side to the perpetual night side. Unlike Earth, with its shifting climates and seasons that drive cycles of survival and extinction, K218b provides a globally stable oceanic environment where life can dedicate itself entirely to growth, adaptation, and complexity. What makes this discovery more profound is the philosophical implication it carries. For centuries, humans have sought Earth twins, planets with rocky surfaces, thin nitrogen-oxygen atmospheres, and shallow oceans. K218b shows us that we may have been looking in the wrong place. Habitability is not defined by resemblance to Earth, but by the presence of conditions that allow life to thrive, even if those conditions are completely alien to our experience. A hydrogen ocean world may be more stable, more enduring, and ultimately more life-friendly than Earth itself. It suggests that the galaxy may be filled not just with rocky Earth-like planets, but with oceanic super-Earth, where life has had trillions of years to evolve in stable, nourishing environments. The hydrogen ocean of K218b is more than a planetary curiosity. It is a new paradigm. It reveals that the universe creates life-friendly conditions in ways that defy our expectations, expanding the boundaries of what we call habitable. In this vast alien sea, where hydrogen and water blend into a medium unlike anything on Earth, life has not only found a foothold, but thrived on a planetary scale. And in doing so, it has shown us that we must reimagine what a living world looks like. The discovery of this hydrogen ocean does not simply prove that life exists elsewhere. It proves that the most life-friendly environments in the universe might be the ones we once overlooked. The atmospheric chemistry of K218b reads like something pulled straight from the pages of science fiction, but the James Webb Space Telescope has confirmed that it is real, complex, and brimming with implications for life. Unlike Earth, where our atmosphere is a relatively simple mix of nitrogen and oxygen, with trace amounts of other gases, K218b's atmosphere is dominated by hydrogen, laced with methane, carbon dioxide, and water vapor, and marked by exotic processes like diamond rain forming in the upper layers. This composition is not only alien to us, but also surprisingly stable thanks to the planet's unique balance of pressure, gravity, and temperature. What stands out most to scientists is the presence of gases that should not exist together in such large quantities without active replenishment. Methane, for instance, breaks down quickly when exposed to ultraviolet radiation, meaning its persistence in the atmosphere is strong evidence of continuous biological activity. On Earth, methane comes from wetlands, microbial digestion, and even livestock, but all of these sources share one key trait: they are alive. To see methane swirling in abundance through K218b's skies suggests that something, or rather countless somethings, are constantly producing it. The absence of ammonia is equally telling in lifeless gas giants. Ammonia dominates the atmosphere, as it is a stable product of hydrogen and nitrogen chemistry. But on K218b, ammonia is conspicuously missing, a sign that biological processes may be consuming or transforming it into other compounds. The chemical imbalance between methane, carbon dioxide, dimethyl sulfide, and water vapor paints a picture of a biosphere actively shaping the air around it. On Earth, our own atmosphere is kept in disequilibrium by life. Oxygen and methane should cancel each other out, but they persist together because living organisms are constantly replenishing both. K218b mirrors this same fingerprint of life, only in a completely alien mixture that suggests metabolisms based not on oxygen, but on hydrogen and methane. Beyond biology, the atmospheric dynamics themselves are extraordinary, because K218b is tidally locked. One side of the planet faces perpetual daylight while the other is locked in eternal night. Normally, this would create extreme temperature differences, boiling the day side and freezing the night side into a lifeless wasteland. But the thick hydrogen atmosphere redistributes heat with such efficiency that temperatures remain stable across the entire planet, hovering around 120 ppf, perfect for maintaining liquid water and supporting life on both hemispheres. This means that the entire planet, from the blistering day side to the frigid night side, could be habitable. Winds move chemical compounds between regions, creating global circulation patterns that spread water vapor, methane, and carbon dioxide across the atmosphere. Such constant mixing not only sustains stability, but also ensures that biosignatures like dimethyl sulfide are detectable on a planetary scale rather than being confined to isolated pockets. Adding to the surreal chemistry is the phenomenon of diamond rain. Under the immense pressures of K2018b's atmosphere, carbon atoms compress into crystalline structures that fall as microscopic diamonds, glittering like snow before dissolving deeper in the thick atmosphere. For life adapted to these conditions, this would not be extraordinary. It would be part of the natural weather cycle. But for us, it's a reminder that alien worlds follow rules that Earth never prepared us to expect. Similarly, methane and carbon dioxide interact under the extreme conditions to form exotic compounds, possibly fueling biochemical pathways completely unlike anything seen on Earth. Radiation, often the enemy of habitability, is another area where K218b's chemistry provides a natural advantage. Red dwarf stars, like K218, are infamous for violent flares that can strip atmospheres bare. Yet the hydrogen envelope on K218b serves as a shield, absorbing and diffusing high-energy particles before they can sterilize the surface or oceans below. This protection means that even if life began in vulnerable oceans, it could eventually spread into the atmosphere, shaping its chemistry on a global scale. What makes K218b's atmosphere so revolutionary is that it suggests life may not just survive in alien environments, but may thrive by exploiting chemical possibilities beyond our imagination. Where Earth life depends on oxygen, K218b may host organisms that use methane as an energy source, metabolize hydrogen, or even incorporate diamond-like carbon structures into their biology. The sheer chemical diversity creates possibilities for ecosystems with complexity equal to or greater than our own. This discovery forces us to abandon the narrow assumption that habitable worlds must look like Earth. Instead, it proves that habitability is written into the chemistry of the universe itself, capable of manifesting in environments that once seemed too alien to consider. The atmosphere of K218b does not just suggest life, it suggests an entire biosphere thriving in ways that challenge everything we thought we knew about biology. The star K218 is unlike our familiar sun, yet it may be far more important in the story of life across the universe. Classified as a red dwarf, it is smaller, cooler, and dimmer than our solar beacon, but those qualities that seem modest at first glance actually make it a near-perfect host for life-bearing planets like K218b. Red dwarfs make up nearly 3/4 of all stars in the Milky Way, meaning that they are not rare exceptions but the cosmic rule. They burn their nuclear fuel so slowly that they can shine not for billions, like our sun, but for trillions of years, lifespans that outlive the current age of the universe many times over. This remarkable stability means that worlds orbiting red dwarfs are given time frames beyond imagination to foster life, allowing biology to take root, evolve, adapt and thrive with no looming expiration date from a dying star. While our sun will eventually expand into a red giant, scorching Earth to a lifeless husk, K218 will remain steady for epochs longer than humanity can currently comprehend, providing its planets with unbroken energy for nearly eternal spans. The relationship between K218b and its red dwarf host is particularly fascinating because of tidal locking. The planet completes an orbit in just 33 Earth days, keeping one face forever pointed toward its star, while the opposite side remains in perpetual darkness. At first, this seems like a recipe for disaster, one hemisphere scorched, the other frozen solid. But thanks to its thick hydrogen-rich atmosphere, heat is redistributed evenly across the entire globe. The day side glows under endless sunrise, while the night side is bathed in perpetual twilight, yet both maintain a stable temperature around 120. Instead of being a weakness, tidal locking creates two distinct but habitable realms that could support a diversity of life. Organisms on the bright side might adapt to constant radiation and warmth, while those on the dark side could thrive in dim, stable conditions illuminated only by the faint glow of stars or auroras rippling across the hydrogen sky. The stability of K218 itself is another crucial factor. While many red dwarfs are notorious for violent stellar flares, outbursts of radiation powerful enough to strip atmospheres and sterilize nearby planets, K2018 is considered relatively quiet and well-behaved. Its flare activity is far less intense than its kin, meaning that the planets in its orbit are not bombarded with lethal radiation. And even when smaller bursts do occur, K2018b's thick atmospheric blanket absorbs the damage, protecting the surface and ensuring that biological processes can continue uninterrupted. This protective buffer, combined with the star's inherent calm, allows K2018b to maintain conditions far more stable than Earth's, where seasonal changes, ice ages, and solar variability often reshape the climate. The sheer prevalence of red dwarfs magnifies the significance of K2018. If this single star hosts a potentially life-rich planet, then the odds are astronomical that countless others across the galaxy do as well. With red dwarfs making up the majority of stars, the chances of habitable planets orbiting them skyrockets. This reframes our entire search for extraterrestrial life. Instead of focusing exclusively on Earth-like planets around Sun-like stars, scientists now realize that red dwarfs might hold the majority of habitable real estate in the universe. K2018b could be one of billions of similar worlds orbiting quiet, stable stars that will burn steadily for trillions of years, providing unimaginably long windows of opportunity for life to flourish. The implications for complex life are staggering. On Earth, it took nearly 4 billion years for single-celled organisms to evolve into the complex ecosystems we know today. If planets around red dwarfs have had similar or greater timescales, they may have nurtured life far beyond our level of sophistication. Civilizations could have risen and fallen countless times over the trillions of years that these stars remain stable. K2018, with its quiet energy and reliable lifespan, may be nurturing life that is already ancient by our standards, possibly more advanced than anything we can conceive. Ultimately, K2018 is not just a dim red star in the Leo constellation, it is a symbol of what the universe may favor. Stars like it are the most common in existence, and planets like K2018 may be the most abundant havens for biology. Our sun, blazing bright but fleeting, may be unusual in its brevity, while red dwarfs like K2018 embody the cosmic patience required for life to take root everywhere. The discovery of K2018 may be orbiting such a star does not just expand our understanding of habitability, it forces us to accept that the universe's most life-friendly environments might not orbit stars like our own, but stars far smaller, dimmer, and longer-lived. K2018 is more than a host, it is a promise that life in the universe has all the time it needs. The discovery of K2018b and the revelations offered by the James Webb Space Telescope represent a turning point, not just in astronomy, but in the human story itself. For as long as we have existed, humanity has stared up at the night sky with the same question echoing in our minds: are we alone? That question has shaped myth, religion, science, and philosophy across every culture and every age. And now, for the first time in history, the answer is no longer hidden in speculation or poetic wonder. It is written in the atmospheric chemistry of a planet 120 light-years away, carried across interstellar space in the faint glow of molecules that should not exist without life to produce them. Dimethyl sulfide, methane, water vapor, carbon dioxide, each of these signatures tells a story of a biosphere breathing and evolving under alien skies. With 99.7% statistical confidence, the data show that life is not confined to Earth. The cosmos is alive. The implications stretch far beyond the realm of science. If life exists on K2018b, thriving under conditions we once thought impossible, then the universe may be teeming with worlds far stranger and richer than we ever dared imagine. This realization rewrites our definition of habitability itself. No longer is the search restricted to Earth-like twins orbiting Sun-like stars. Instead, hydrogen-rich super-Earths orbiting long-lived red dwarfs may be the true cradles of life in the galaxy, providing environments more stable and nurturing than our fragile blue planet. That discovery alone changes how we see ourselves. Earth is no longer unique, but part of a vast continuum of living worlds, each shaped by its own chemistry, atmosphere, and stellar companion. Life is not the exception. It is the rule. But beyond the scientific wonder lies a deeper psychological and cultural shift. The confirmation that we are not alone ends humanity's cosmic loneliness, a solitude that has defined us since our species first looked up at the stars. Knowing that life exists elsewhere forever alters how we perceive ourselves, our place in the universe, and even the meaning of our existence. No longer is humanity an isolated accident. We are participants in a galactic story of biology, evolution, and survival. Every child born after this discovery will inherit a new worldview, one where the universe is not an empty void, but a thriving ecosystem stretching across light years, where alien oceans, skies, and landscapes hum with unfamiliar but undeniable vitality. This conclusion also demands responsibility. If the cosmos is alive, then our actions as a species take on a new weight. We are no longer just guardians of Earth, but members of a broader community of living worlds. The ethical questions are immense. Should we attempt to contact life beyond our planet? Do we have a duty to protect alien ecosystems from interference, contamination, or exploitation? As space exploration advances, these questions will become more urgent, shaping international policies, technological decisions, and perhaps even spiritual beliefs. Just as Earth's biosphere is fragile, so too might be the delicate atmospheres and ecosystems of other planets. The recognition of life beyond Earth compels us to act with humility, caution, and reverence. And yet, alongside caution comes inspiration. For the first time, we can look into the void and know that the universe is not indifferent. Life has emerged elsewhere, shaped by different conditions, but bound by the same fundamental chemistry that governs us. This points to a universality of biology, suggesting that life's building blocks are written into the very fabric of reality. In that sense, the discovery is not just scientific evidence, but a cosmic affirmation that life is inevitable wherever conditions allow. The dimethyl sulfide drifting in the skies of K218b is more than a chemical signature. It is a whisper across the stars that says, "We are here." The James Webb Space Telescope has given us the first glimpse of this truth, but it will not be the last. Future observatories, more powerful and precise, will expand this catalogue of living worlds, mapping a galaxy where life is not rare but abundant. Soon we may not just confirm biological activity, but glimpse signs of civilizations, technologies, or evolutionary paths beyond imagination. The conclusion we reach now is only the beginning of a broader awakening. Humanity is standing at the threshold of its greatest transition, from a species confined to one planet to citizens of a living universe. In the end, the story of K218b is not just about one planet or one discovery. It is about the breaking of an ancient barrier, the moment when speculation gave way to certainty. For all of human history, we have carried the weight of believing we might be alone. That weight is gone. We are not solitary wanderers in a dead cosmos. We are part of something far larger, richer, and more profound. The conclusion is clear. Life is not unique to Earth, and the universe is not silent. It is alive. It has always been alive, and we are only just beginning to listen.